Chapter 12, slides 32 to 43. Okay, so now we have covered how to make alcohols, right? And we've also done a little bit of what we can do with alcohols. So just to recap, we can make alcohols from double bonds, or we can make them from carbonyls, right? These types of functional groups can lead us to the alcohol functional group. Okay, so you can start with a carbonyl of some variety, you can start with a double bond, and you can make an alcohol from those two functional groups. We also just covered the fact that alcohols can become carbonyls. So we know how to turn them back into carbonyls, okay? But for these slides, we're gonna focus on alcohols again as the starting material, but instead of getting to the carbonyl, we're gonna do other chemistry with it. We have used alcohols under acidic conditions, acid-base chemistry, to protonate them and make them into better leaving groups. And then basically do SN1 chemistry on them. So we've seen this chemistry before. So we've been able to take an alcohol and do SN1 chemistry. But if you remember, SN1 chemistry is kind of hard, right? Because it's always competing with E1 and it's a little tougher to control. So maybe it'd be better if we could use alcohols in an SN2 reaction. Okay, so how do I use alcohols in an SN2 reaction? Here's an example where I'm trying to run an SN2, and this is why you did not see alcohols in SN2 chemistry. SN2 chemistry tells me I need a strong nucleophile, so I need a strong negatively charged system. But remember, a strong nucleophile is also a strong base. And the problem with doing SN2 chemistry with an alcohol is that if you start with a strong nucleophile / base, alcohols have a protic system, right? There's a proton there. And as discussed, the pKa of these guys are around, 15 to 19. So this is a problem because when you're competing between being a nucleophile and being a base, plucking off a very electropositive, if you think about the electropositivity here, this is a very electropositive atom, and it's super easy to pluck off because of the lack of steric hindrance. Versus, yes, that carbon is, due to the dipole between carbon and oxygen, also partially positive. However, the difference in polarity between oxygen and hydrogen makes the hydrogen way more electrophilic than the carbon. We're not saying the carbon isn't electropositive, but in a competition, acid-base chemistry is going to prevail because of the attraction. So if you're trying to do SN2 with a strong nucleophile, it's not going to behave like a nucleophile. It's going to do acid-base chemistry, and it's not going to do what you want it to do. Since we have covered now more than 10 ways of making alcohols, we know how to make alcohols a lot of different ways from a lot of different functional groups. So wouldn't it be nice if we could make an alcohol, change it into a good leaving group, and then do SN2 chemistry? So that's what we're going to focus on. The fact that we know so many different ways to install an alcohol, that just says, all right, well, let's turn alcohols into better leaving groups and then do what we want to do with them. So we're going to start with the first thing that chemists thought of in trying to convert an alcohol into a good leaving group. Like ethanol. And we could hit it with something like HBr or HCl, some really strong acid. And we're going to do the chemistry that we've done in the past. We're going to protonate the alcohol using the very strong acid. And then, depending upon the substitution of my alcohol, I could employ SN1 or SN2. Right now, I have a Br- floating around, and you could say, since it's really not sterically hindered, you could exchange this out. So if you started with a primary alcohol, we're going to do acid-base chemistry followed by the SN2. I could have started with a protonated tertiary alcohol, and because it's tertiary, the leaving group leaves, I form a carbocation, and then the Br minus attacks. Either way, actually it's not forming the same compound. Either way, I end up with the bromine where the alcohol once was. Now, understandably, you could have a lot of things go wrong in this. All right, so the limitations of just hitting it with a strong acid like HBr or HCl so that it exchanges out for the halogen, there's a couple things here going on. You get very poor yields. Okay, this may not be difficult to think about. I mean, what you've done is you started with an alcohol and you ended with a bromine. Well, arguably, the bromine is a better leaving group than the alcohol, and in whatever conditions you're using, maybe you've just thrown water off. Water could probably want to reverse back. So this is a reversible type reaction. So you might not favor the product largely. So we see poor yields overall. And we see even poorer yields when using HCl to form alkyl chlorides. There are limitations because if you're doing secondary or tertiary systems and you're hoping for SN1 to govern the mechanism, you're going to compete with elimination because SN1 competes with E1. Now you're going to get some double bonds in there. If you're doing SN1 type chemistry under these strongly protic acidic conditions, you might get rearrangements. Maybe that's not what you wanted. Maybe you worked really hard to put an alcohol exactly where you needed it so that you can use it as a leaving group, and then rearrangements occur and now it's, screwed up the whole carbon skeleton you were hoping for. There's also little reactivity with HI. So if you wanted a better leaving group like iodine, you're not going to get that. And you're using strong acids at the end of the day. HBr, HCl, not super compatible with a lot of functionality around, right? So here's what I'm going to do here. I'm going to say this is theoretically, where people start. How do we turn OH into a better leaving group? But you're never realistically going to see me use this. I have never run this reaction in a lab. It's just sort of a theoretical construct to think about. Like, yeah, how could we change OH using what we know into a better leaving group? Practicality-wise, let's just put a big X through this one. I don't even need you to make a flashcard of this. This is just sort of a lesson in, philosophy and thinking about how you could. Can you do it that way? Sure. Is it practical? Not really. So let's just put an X through it. I don't need you to make a flashcard and think about this reaction anymore. But I do want you to think about the product that we're trying to attain. We're trying to convert the OH into a better leaving group, like a bromine, right? So at the end of the day, leaving groups that avoid these protic issues are things like chlorine, bromine, and iodine. They don't have a proton, so they're not going to compete with acid-base chemistry. So what I want to focus on now are practical ways of converting your alcohol into a halogen, because we already know that those are good leaving groups. So ultimately what I'm trying to show you is if I can install an alcohol, right, as let's just do a little synthesis here. If I have a carbonyl, I can reduce it with sodium borohydride to an alcohol. I want to know how I can turn that alcohol into a better leaving group so that I can do SN2 chemistry. Okay, so this is what I'm trying to do. We've discussed how to get here, and now we're focusing on how to convert realistically the alcohols into better leaving groups. The first one I'm going to show you is with PBr3. So this is a new reagent. And if you look at the functionality, I've got an alcohol here with a stereocenter. And if you look at the mechanism, you see it's SN2 followed by an SN2. Well, let's take a look at how this works. I could start with this alcohol, and PBr3 is a molecule like so. Phosphorus, if you recall, is like nitrogen. It's in group 5. It has 3 bonds and a lone pair. However, with these 3 bromines around it, right, the dipole of it's trigonal pyramidal, not trigonal planar. And so it has a dipole moment, and that phosphorus is electrophilic because of all the electron withdrawing bromines pulling electron density away from it. So our positive phosphorus is going to undergo an SN2 with the oxygen. Okay, so here's our first SN2. We lost one of the bromines. Okay, here's our second SN2. The bromine now acts as the nucleophile, gives the electrons back to the oxygen. This whole thing is a great leaving group, right? This whole thing is your leaving group. And the bromine, because it did an SN2 at that carbon, is now inverted. So we started with the alcohol in the front, we ended with the new leaving group in the back. So, benefits to this reaction. Because you're doing an SN2 reaction, okay, you are not seeing any rearrangements. So you don't have to worry about any rearrangements occurring. You can actually use PI3 and get alkyl iodines, right? So an iodine is possible through this method. You also get pretty good yields from this method. It's a pretty easy reaction to run. And I'll add that you're keeping the pH of this system pretty low. Right? It is going to be fairly neutral. You're not using strong acids. So it's very amenable to a lot of other functionality in your system. The problem, the only limitation I see in this one is the fact that you're limited by the electrophile. So the carbon we just attacked is secondary, and you really can't go much more than this. Because the reaction is governed by an SN2, we have to avoid steric hindrance. Otherwise, the SN2 reaction just doesn't work. So if this was a tertiary alcohol, this reaction wouldn't work very well. What do you notice about the overall transformation when I use PBr3? Well, it's all about your design. If you designed the alcohol with the configuration in the beginning as forward, you're going to flip it. So it's going to invert overall. So understand that if you are now going to use this reaction in your own SN2, maybe you want to now use that carbon minus from the alkyne, you know, you've deprotonated that and want to add more carbons, understand that if you're doing an SN2 now, that would be your final product, right? And so if you started with the alcohol in the front, you're changing it to a better leaving group, you're going to end, because you're doing a series of negations, right? You're doing an SN2, flipping it, doing another SN2, flipping it. And so you end up with, you have to kind of figure out the inversion sequences of doing this SN2 followed by an SN2. So understand that, you know, from start to finish, you have to plan the stereocenters very well, understanding what each step of your pathway does to your system. All right, what if I wanted the alkyne in the back? You know, what if I wanted that? Is there a way to do that? Well, you could have started with the other alcohol, right? But what if that was the alcohol that you made and you had it in large quantities? Is there a different approach? Well, yes, there is. We could look at something like SOCl2. And this is a kind of a tougher mechanism, but let's see what happens here. Let's say I started with the alcohol. Drawn in the same configuration. We're going to use something called thionyl chloride. Stuff is nasty to work with. And typically, the one that I'm going to show you is run neat. What that means is that you maybe you can use dioxane solvents or something like that, but I've mostly run these reactions neat, meaning I have an alcohol that's a liquid, and I have thionyl chloride, which is a nasty liquid, and you just kind of use them together without a solvent system. What happens here, and I'm going to do an SN2. Okay, so this was my SN2. I'm going to talk a little bit about what I just did here in a second. Why didn't I do a 1,2 addition? Talk about that in a minute. Sort of a cheat, if you will. Okay, now I'm here. All right, so I just did the SN2. The oxygen attacks the very electrophilic sulfur. I mean, look at the dipole of that sulfur, right? The sulfur has 2 chlorines off of it and a carbonyl, well, not a sulfonyl, a sulfone type structure to it. So it's very electrophilic because it has these electronegative atoms withdrawing electron density away from it. Okay, so we're going to do an SN2 on the sulfur, and we're going to come back to why I'm doing an SN2 and not an in, up, down, out. Okay, so at this step, we're going to use the chlorine to remove the extra proton, do a little acid-base cleanup here, a little in-between. And we're at this structure here. Okay, now here's what occurs. I'm going to call it an SN1-like reaction. In the literature, it's called, it actually has a name, SNI. SNI is an ipso substitution. And I've posted a really fun discussion for you guys to look into called the SOCl2 discussion. And what's funny is that this ipso substitution was the only way I ever learned. And in fact, I've run these types of reactions before. And I didn't, until I started teaching, I didn't recognize what a crazy debate this was. And I guess I just didn't notice how it was portrayed in the textbook. So if you go looking for answers in your textbook, you're probably not going to see, it's going to gloss right over the mechanism, no discussion, they don't want to talk about it. So I've posted the discussion online of scientists talking, and actually one of them is my friend Rico, who was like, he and I went to school together, so we learned very similarly. And like I said, I've done these reactions before, so they operate in this SNI ipso substitution. So what the heck is that? Well, you can liken it to an SN1 type scenario. What happens is that this reaction is governed thermodynamically by the formation of SO2 gas. Can you see it's like almost like carbon dioxide, right? It's sulfur dioxide, SO2 gas. And you've got a good leaving group still. So what happens is that if you've got a secondary or tertiary alcohol, the leaving group will leave. So these electrons will go here. You can see that it'll form that pi bond to make sulfur dioxide. And then the chlorine will get kicked out in this process. It's like an exchange. Now here's what's interesting about it. The SO2 gas bubbles away, right? That's going to bubble away. But what you've done is you've created a carbocation. Now you could say, well, it'd be SN1. The chlorine can attack the front or the back. But here's the kicker. In the past, when we have done SN1, the nucleophile has always been external to the leaving group. The leaving group leaves, you form a carbocation, and then it was the solvent, which was everywhere, that could come in from the front or the back. Why? Because the solvent's everywhere. Here, the nucleophile is not everywhere. It's like the nucleophile gets dropped off on the front face because this is the front, right? So this group leaves from the front, dropping the chlorine off right in the front of the molecule. And they have this intimate association. Okay? You get dropped off in the front, you're not going to be like, let me wander around to the back of the molecule to attack. No, you get dropped off and immediately you're associated and attracted to this positive charge from where you just got dropped off. So if you just got dropped off in the front, because you're only going to have a nucleophile available when this leaves, right? As it leaves, it's dropping off the nucleophile right on the face that it's going to do the attacking. So you actually get retention of configuration. Whether the book shows this or not, like, it varies from book to book. And so I urge you to read this article because he actually does a review at the end of each organic textbook out there. Not all of them, it's not comprehensive, but of each textbook out there and how each textbook covers this reaction. But SNI, ipso substitution, or if you just want to say it's very similar, right? Leaving group leaves, nucleophile attacks. The only difference of it not being an SN1 is that you don't typically get rearrangements, and you're going to get the substitution, the nucleophilic substitution from the same face as the leaving group was. So you get retention. You get good yields for this reaction. And it's one of the best methods to generate alkyl chlorides. But the limitation is, because you're forming a very quick carbocation type system, it only works on secondary and tertiary alcohols, not on primary alcohols. So I can convert the OH into a good leaving group and maintain the stereocenter. So when I want to do my SN2 of, say, my strong nucleophile in the next step, can do an SN2 and I can obtain that backside product that I was aiming for in the previous case. So what this is doing is it's giving me an arsenal of methods to think about how I can use stereochemistry to afford the desired product that I'm trying to make. Now, here's what a lot of books do, and they don't discuss it. Okay, so I just want you to be aware of it. I've never run an SOCl2 with pyridine or triethylamine before. And I guess if I was aiming for an inversion, I would just use PBr3 because I've had good luck with that, good yields. So I just want you to be aware that many books, even online, I don't know if you're using Khan Academy, but you've got to pay attention to if they add an amine, because this changes the whole system. Notice that it's an SN2 now, actually with a sort of a 1,2 in the middle. So I'm just going to show this to you quickly. You start with the thionyl chloride. Things start off okay. They're the same. I'm going to do my SN2. I'm going to talk about why I did an SN2 here in a little bit later. Okay. And so, yeah, you've got this chlorine minus hanging around, but when you have triethylamine is a great nucleophile and base because it's not greedy, right? It's got electronegativity, it has the lone pair, but it's not super electronegative, which means it's much more generous as a nucleophile slash base. That's why amines are basic as a functional group goes. So the triethylamine is added to the system, and so it's buffering. It can deprotonate, but it will also do this. And this is what stops the ipso substitution from occurring. It's sort of, it stops the SNI from happening. Okay, and we end up here. And what happens next is that it's like the nitrogen hijacks the chlorine's job. The chlorine is now not the only player in town. And so it gets to this point. And at this point, the chlorine has to come to the rescue. The chlorine's job was taken over by all of the triethylamine around, but now it's set up for the chlorine to do an SN2. And you can see now that the chlorine came in from the back. It reestablishes your triethylamine, and you generate your SO2 gas. Right, so there's your SO2 gas again. You're still generating that. So you have to just be very careful. So I'm going to say with homework and such, be careful of the reagents declaring an amine. You could have triethylamine, you could have pyridine. They're all amines. They all do the same thing. Okay, pyridine, it's an amine, okay? It changes the game. When I test you guys, you already have a way of achieving inversion from an alcohol to a better leaving group via inversion called PBr3, right? I already showed you that. This one is if you have to choose between using thionyl chloride and PBr3 all day long, it's so much easier to use. Thionyl chloride smokes and is reactive and is nasty, and you're generating, bubbly gases, and I don't know, it's just kind of messier to use. PBr3 is much more of a dream. So between the two, choose PBr3 if your goal is overall inversion from an alcohol to a halogen. If you want to retain stereochemistry, thionyl chloride on secondary and tertiary systems is the way to go. This is more of an FYI, and I'm not going to test you on it to be tricky. I just want you to be aware, so when you're doing your homework, be aware of them adding triethylamine or pyridine to your reagents. Then you're actually going to follow the SN2. Now we have a few other methods. Now for the book Klein that we're using, this comes in, they actually introduced this chemistry in an earlier SN1, SN2 chapter 7. But I don't think it belongs there. Too much, too soon. I think now is the time to show you all of our tricks of converting alcohols into better leaving groups. So I'm going to introduce these very widely used leaving groups that are very easy to make. And they're called mesylates, tosylates, and triflates. And they are listed down below in order of their ability as a leaving group. So for instance, you know how iodine is a better leaving group than bromine is a better leaving group than chlorine. Well, triflate is a better leaving group than tosylate is a better leaving group than mesylate. They kind of have their own sort of trends, very similar to iodine, bromine, and chlorine. And we'll talk about why we see this trend for them after we see how they get put onto alcohols. All right, so what you're going to notice is these are very easy to mechanistically to see. You're going to do an SN2 followed by acid-base chemistry. Let's use the same substrate. All right, and they all work the same way. So, I mean, take your pick. Let's make a triflate. So you go to the store and you buy some chloride of the triflate. Okay, and we're going to do our SN2. The oxygen attacks the sulfur, kicks off the chlorine. And then the triethylamine acts as the base to buffer. So here's your acid-base chemistry. And you have just made a triflate. And these are great leaving groups. Okay, now you might be asking, well, in that previous one, we saw the triethylamine attack the sulfur and kick off. Well, CF3 is not a good leaving group. Okay, the first leaving group, this SN2 that we did, that kicks off the best leaving group. Once you do that, the triethylamine doesn't really have a means to attack the sulfur anymore because there's no good leaving group other than the reversible oxygen. But sulfur oxygen bonds are really strong, so you're not going to kick off that sulfur oxygen bond either. So because triethylamine is a little bulky, you're also not going to do SN2 chemistry with it either. So you don't really have to worry as long as you're using these gangly, bulky amines, right? It's not a good SN2 nucleophile. That's why we're not in competition here. That is not going to happen. Okay, you're not going to have the nucleophile the amine act as a nucleophile because it's so bulky. So it's just there as a proton sponge. This is your buffering base, right? I call them proton sponges. They're just there to keep the pH buffered and to pluck off any residual protons needing plucking. And there you have it. This is the same mechanism for each and every one of these. The mesylate, you can see the only difference between any one of these is the group off of the sulfonate. So you can see the alcohol, whatever your alcohol is, attacks the sulfur, kicks off the chlorine. Attacks the sulfur, kicks off the chlorine, right? We just did the triflate above. So it's an SN2, and then the proton sponge amine comes in and just plucks off the extra proton. And voila, you're done. Okay, what you'll notice is that we have just made a really good leaving group. The triflate, the tosylate, the mesylate, any one of those. What you'll also notice is that the alcohol's stereochemistry was retained because all the chemistry happened up at the oxygen and nothing happened at the carbon. Our electrophilic carbon remained intact throughout the whole thing. Nothing happened to that bond, okay? So if you want to keep stereochemistry and convert your OH into a better leaving group, one of these could be the winner. So these tosylate, mesylate, triflate groups are great leaving groups. Why? Why are they good leaving groups? Well, let's take a look at one of them. Let's say we just made that triflate from the previous slide. Okay, and I want to take my alkyne, that deprotonated alkyne is my strong nucleophile, and do an SN2 reaction on it. Why is that whole thing? Why is this thing right here? Why is it a good leaving group? Let's analyze it after an SN2 reaction. Well, the alkyne would have come in from the back because it did an SN2, and the leaving group is O minus. Had the leaving group been a tosylate, this would have been the leaving group. And had it been a mesylate, this would have been the leaving group. So let's look at this. I'm analyzing the leaving group. What gets kicked off has a negative charge. You guys know, you guys have a tool to analyze the stability of a negative charge. It's called ARIO. ARIO is going to help us qualitatively understand the stability of what left as a negatively charged species. So they're all oxygens. So as atoms go, oxygens are electronegative. So that's decent. But you know, OHs are not great leaving groups. So what makes these extra better? Well, they have resonance, right? You can draw resonance structures in a couple different directions. Lots of resonance structures for all of these. They're all O minuses. They all have resonance. Now, induction is what makes these different according to one being a better leaving group than another. And to do that, we have to look at the groups that are farther down the line. So we're going to look at induction. CF3 is an electron withdrawing group. And electron withdrawing groups nearby to a negative charge are good. They help stabilize, right? The benzene ring can be considered also an electron, well, I'd say it's a weak electron donating group. It could be electron withdrawing groups depending upon how it is organized, given the fact that it is conjugated. You can see the double bond here, single bond, double bond. It's in conjugation, so it can be considered a weak donating group or a weak withdrawing group. It is just a cloud of carbons and hydrogens, so it's a weak electron donating group. But right now it's in conjugation with the pi system, so it could also effectively be a weak electron withdrawing group. It's kind of in between. A methyl group is definitively a donating group, but it's a weak one. So we're not throwing really strong donating groups at those positions. They're weak. So the best one is the CF3. The next best is when you have a little bit of withdrawing character because of conjugation, and the electron donating group in the methyl doesn't do anybody any favors, but just without it, even it being there, still makes the mesylate a decent leaving group. So you can understand now why, going back to this slide, why the triflate with its electron withdrawing group is better than having this, which is just mildly withdrawing, and much better than the mesylate, which has a donating group. So stabilizing the negative charge left behind when you use it as a leaving group can be explained using ARIO. Now, why is the mechanism that I showed you in SN2? And I hinted at the fact that it's sort of a cheat. And again, if you go to your textbook, they do not show you this mechanism. They don't show you, when I say this mechanism, they do not show you this mechanism right here. I think that it is because there is a lot of wishy-washiness when it comes to atoms like sulfur and phosphorus. So I just want to make this point that, you know, we push electrons through this course. And I often tell you that organic chemists get made fun of for our electron pushing, you know, oh, you and your electron pushing formalisms. But they are ways of accounting for what's going on. I mean, electrons exist. They are what make up these bonds. They can't be created or destroyed. They don't just disappear, and things don't magically happen. We can rationalize how things occur. But sometimes people are very reticent to state firmly, this is the mechanism, right? So what I'm going to propose here, and this is going to explain a little bit when you go into biochemistry as well. When you have carbon, and carbon has a carbonyl, and you have a nucleophile, you're going to do in and up. And you're going to form a tetrahedral intermediate. This has to happen. Let's take a look at the periodic table. Now in the periodic table, look at where carbon is. Look at the electron configuration for carbon. What is its outermost shell? 2, right? You've got a shell of 2. So its outer shell is 2. Is there any such thing as a 2D set of orbitals? No. So carbons, 1s2, 2s2, 2p2, its outer shell is shell 2, and shell 2 has no d orbitals. You have to, from an orbital perspective of what's allowed, when the nucleophile makes a bond with the carbon, it has to come in and break the pi system and make way orbitally to make sense. So this is the only way you can do it. All right, I'm going to draw a wall here. I'm going to make a claim that when you're dealing with things like sulfur, phosphorus, right? Those atoms are in the, let's take a look at the periodic table again. Look at their electron configuration. 1s2, 2s2, 2p6, 3s2, 3p for phosphorus, 3p3 for sulfur, 3p4. So what we're saying is sulfur and phosphorus have an outer shell of 3. Is there such thing as 3d orbitals? Absolutely, right? Remember, the next row of d orbitals is 1 minus, so it's n minus, so it's 3d. We also know this because sulfur, you've seen this. Sulfuric acid, right? When you guys do ATP stuff, you're going to see these phosphonates. Count the number of electrons around sulfur and phosphorus. They have expanded octets. Why? Because they have d orbitals. So even though when you're doing the electron configuration, phosphorus and sulfur, you're not going up to the Ds, they still are there. I say it's like sulfur and phosphorus have an attic. They didn't put anything in the attic, but the attic is still there just because you're not storing anything in it. So when you do the electron configuration, it has a 3 shell. Shell number 3 is the outside. It has 3d orbitals which it can expand and use. Thus, the orbital configuration for sulfur and phosphorus is indeed different than carbon. And this is why I am not showing you an in-up 1,2 substitution definitively for sulfur or phosphorus or chromium. Chromium definitively has d orbitals, right? Chromic acid, when we were doing oxidation, I had you protonate the oxygen and then I had the alcohol do an SN2. I allowed you to do that because chromium has d orbitals and we do not have to follow the 1,2 substitution tetrahedral intermediate. Okay, so what you're going to see is that I'm going to allow us to do SN2 reactions. There's evidence in papers in the literature purporting that in enzymatic conditions in biological systems, SN2 is more likely the case for these and that they're not going through tetrahedral intermediates. Who knows, right? But if things can be figured out using a much easier one and done SN2 mechanism, I'm going to allow you to do that for sulfur and phosphorus, specifically because of their d orbitals. Okay, but I can never let you do that for carbon. So that's why in these reactions, when we had an OH and I was using these, let's say the mesylate, I'm making a mesylate from mesyl chloride, I'm not doing in, up, down, out. I'm allowing you to just skip to the chase. Why? Because sulfur has a d orbital. Okay, so we're going to be allowed to do these SN2s on these systems. You're probably going to go into biochemistry and see ATP, ADP chemistry, where they're going to have a nucleophile attack the phosphorus and immediately kick out an oxygen, and they're not going to do in, up, down, out. And you're going to go, whoa, biochemistry teacher, you're supposed to do a 1-2 addition there. They might shove a paper in your face and say, through enzyme chemistry, you're allowed to do this. But I'm just going to say d orbitals, let's just let it slide. Let's just perform an SN2. What I never, ever, 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 ever want to see you guys do is this. Please, never, ever, ever. It can't be done. You're not allowed to shortcut this. This is not up for debate. You cannot, on a carbon, you cannot do this. Okay? This is a definitive no-no. It cannot be done. You cannot do an SN2-like system on a carbonyl. No d orbitals. This is a definitive 1-2 addition. In, up, down, out. Okay? I just want to make sure you guys understand the difference and why I'm not doing that with sulfur and phosphorus, or chromium for that matter. I just kind of circumvent it and do an SN2. Much easier. But you cannot do that on a carbon. Carbon does not have d orbitals.
Are we clear?
Yes, sir.
Are we clear?
Crystal.
Okay, here's your practice. We now have multiple ways of making alcohols, and I show you a whole list of alcohols here. It's all the same alcohol. I want you to practice making them into better leaving groups using the methods we've just discussed, and then take that product. Be very careful about your stereochemistry. Be very careful about your stereochemistry and show the product after an SN2 reaction with the following nucleophiles. Okay? All right, drug metabolism. Here's a beautiful example of how converting a bad leaving group alcohol into a good leaving group works in our bodies. A common metabolic pathway called glucuronic acid conjugation, or simply gluconoridation, is a process just like our SN2 process that we've been talking about. Specifically, we start with D-glucose. You can see it in its ring form here. And this bad leaving group, the OH at this position, the anomeric position, is going to get converted into UDP. So notice that you've got this phosphorus, probably does it by an SN2, but it reacts with the phosphorus, kicking out a leaving group and putting this whole big group on here. And this thing is now a better leaving group, because if it leaves as O-, it can be resonance stabilized, just like the sulfur groups were, right? It's very synonymous with the sulfonates that we just made. So this OUDP, good leaving group, is what helps in metabolism. So what happens is that an alcohol will now interact in order to, now this is, we can come back to this in a subsequent chapter, and this is through glycolysis, but what's more likely happening is that this oxygen assists in having this guy leave. And then it attacks from the equatorial position. Much easier to come at from the equatorial position because there's a lot less steric hindrance. And you can see that the alcohol then is displaced. So this is exactly how our bodies would metabolize certain drug compounds like morphine, acetaminophen. You can see they all have alcohols, right? Alcohols that can perform the chemistry. These are all of the alcohols that would act just like the alcohol shown here. And once it forms forms the beta gluconoride, That's how our body can then pass and excrete these molecules. Up until then, the molecules are not processed well by our body. So remember that with all nucleophile attacks, if the goal is to do SN2 chemistry, you still have to remember all your SN2 chemistry. Remember all the things and the limitations about SN2 chemistry. So in this practice that I gave you, I'm converting a secondary alcohol in all of these, right? These are all secondary alcohols. So when you add the strong nucleophile in this last column to do SN2 chemistry, understand we're doing it on a secondary system. Remember to keep that in mind. Even if you have a tosylate, which is a good leaving group, if it's a tertiary tosylate, you know what? You're going to now compete with E2. Tertiary, even if you have good leaving groups, do not do SN2 chemistry well. So we have just simply made alcohols into better leaving groups such that we can do SN2 chemistry. But all of the rules that govern SN2 chemistry, you can't just throw them out the window. Okay? You still have to think about E2 chemistry. So let's say you want the following reaction to occur, but you do not observe your product since OH is not a good leaving group. And this is what we've been doing the whole time. How would you design a route to go from the starting material given to the product shown? Okay, so think about it. You have choices. Here's some more practice in designing pathways to lead from starting material given to product shown.